So, polarography. So, we talked about the various applications of polarography. Now, it has reducible anions such as bromate, iodate, chromate, nitrate. They can also be determined using well buffered solutions. Then, coming to some practical applications of polarography. So, here in table 9.1, different samples or compounds that can be determined by using polarography have been listed here. Like if for the determination of copper, lead, tin, or zinc that is present in different types of food stuff. We can also analyze the presence of copper, lead, nickel, and cobalt present in steel. Also, we can see the presence of riboflavin that as an impurity that is present in milk and pharmaceuticals. Even the presence of vitamin C and fruits and vegetables can also be identified from polarography. So it is polarography is also useful in the analysis of biological systems to determine the presence of different types of vitamins, alkaloids, hormones, terpenoid substances, and natural coloring substances. It is used in analysis of drugs and other pharmaceutical preparations. Now coming to, we'll discuss one by one. So first is the polarographic analysis of organic compounds. So most of the in organic chemistry, it deals with the qualitative and quantitative analysis of the structures. So we know that most of the organic compounds, it is insoluble in aqueous medium and also in mercury to form the corresponding amalgam. So this is, so to develop a easy procedure, the solvent in which the organic compound and its electrode product is soluble, it is added to the supporting electrolyte. Now, solvents such as alcohols, ketones, DMF, acetonitrile, ethylene diamine, and like this, they and the solvents of this type, they are chosen for the analysis of organic compounds by polarography. So the commonly used supporting electrolytes which are easily mixed with organic solvents are various quaternary ammonium salts, such and mostly it is tertiary butyl ammonium iodide. So this is used as a supporting electrolyte. So then here some of the organic compounds that are reducible at the DME. It has been shown in figure table point 2. The like ketone, aldehyde, alkenes, nitriles, azo groups, nitroso, hydroxylamine. So these groups, they can be reduced at the DME. So in also in addition to this, dibromides, aryl halides, alpha halogenated ketones, they can also be reduced at the DME. Even mercaptones like SS, SH, sometimes what happens is they get oxidized at the DME, and hence it is not very easy to analyze such compounds by polarography. Now coming to here in table 9.3, the organic functional group analysis of non-polarographic active groups have been shown. These non-polarographic active groups, they are first converted to polarographic active groups and then they are determined by polarography. So first is, here we can see the carbonyl group. So if we give the reagent Girard T and D, then it forms azomethane. If we react the carbonyl with semicarbazide, it forms the carbazide. If carbonyl group is reacted with hydroxylamine, then it forms the active polarographic group, that is hydroxylamine. So even for such a functional group phenyl, the reagent, if we nitrate the phenyl, by the process of nitration of the phenyl groups, we get the NO2 group, that is nitrophenol. So here this nitrophenol, it becomes an active polarographic group. So in this way, if we ever come across a non-polarographic active group, by reaction with suitable reagents, they are converted to active polarographic groups and then they can be analyzed by polarography. So now coming to applications of amperometric titrations. Now amperometric titrations, we as we have studied, but these titrations, they have wide applications than polarography, because they the even the electro inactive species, they can be determined by converting them into electroactive species. So According to Ilkovic equation, we know that the diffusion current is directly proportional to C, that is the concentration of the analyte, keeping all other factors constant. So, if some of the electroactive material in the solution it is removed by interaction with some other reagent, like mostly EDTA, then the diffusion current decreases. So, this is the fundamental principle of amperometric titrations or polarographic titrations. The diffusion current at an appropriate applied voltage, it is measured as a function of the volume of the titrating solution. The end point is the intersection of the two lines, giving the change of the current before and after the equivalence point. So at the end point, then we can find out before and after the difference, and we can find out the change in the current. Then common examples of amperometric titrations like complexation reactions, they involve EDTA, and many metallic ions can be determined by this complexation process. For precipitation reactions, for example, if we take dimethyl glyoxime, nickel can be identified. If we take silver nitrate, then various types of ions like chloride, bromide, iodide, cyanide, and thiols, they can be identified. Even by oxidation reactions, some of the metals they can be identified. Like if for iodine, if the titrant is iodine, then the species that can be determined is sodium thiosulfate and arsenic, and likewise these are some of the examples. Now coming to polarography experiments. So first is the determination of the nature of the ion, that is the E half. So the half-wave potential of thallium plus ion we will determine by polarography. So here the procedure, it involves some simple steps. First is we will prepare thallium nitrate solution of 0.5 millimolar in KNO zero point 0.1 molar KNO3 supporting electrolyte, and then we will draw 10 ml of this and draw the polarigram. So then the E half can be determined from the reduction wave of the TL plus, and we will compare our obtained value with that reported by other groups. So then we will use this E versus log I by ID minus I, and then we will find out the half wave potential, that is E half. Then coming to the determination of CD2 plus, cadmium 2 plus, that is present in an unknown solution by the use of polarography. So here we will use both the calibration curve method and the standard addition method. So first is the calibration of calibration plot. So to draw the calibration plot, we will prepare the stock solution of cadmium by dissolving 1 gram of cadmium salt. Then we will make subsequent dilutions from this stock solution, and we will add 50 ml of 2 molar KCl and 2.5 ml of 0.2% gelatin. Then we will take 10 ml of the unknown solution and add the same thing, that is 50 ml of 2 molar KCl and 2.5 ml of 0.2% gelatin. Then we will record the polarograms. So first, obviously, then before recording the polarograms, we will pass nitrogen through it, because we know that polarography, it cannot be proceeded in normal oxygen temperature. So for the cell has to be uh, uh, provided with an inert atmosphere, and mostly nitrogen is passed through it. Then the polarogram is recorded. So once we record the polarogram, the calibration curve will be drawn for all the standard solutions, and then the concentration corresponding to the unknown is noted from the plot. Then coming to the method of second addition, the polarograms of the unknown solution is first recorded here as previously, and the second polarogram is recorded by we adding a known amount of the same ion. So here in the second polarogram method, what we will do is we'll take 10 ml of the unknown solution, 5 ml of the known stock solution, 50 ml of 2 molar KCl and 2.5 ml of 0.2% gelatin, and then we will record the polarogram. So then after that, from the plot we will determine the wave height and the concentration of the unknown solution. So these are the two processes. One is the calibration curve method, and second is the second standard addition method, so by which we can determine the amount of cadmium that is present in an unknown solution. Then coming to determination of lead and copper that is present in steel. Mostly in the as impurity they are present in steel. So here the in the analysis the ferric ion that is present in steel, it interferes because of its reduction near zero potential in sodium tartarate supporting electrolyte. So here Fe3 it has to be reduced to Fe2 plus with hydrogenium ion in HCl medium so that Fe2 is reduced at a very much negative potential which is more negative than lead and copper. So the procedure is also very simple. So we will dissolve 5 gram of steel of our sample and 25 ml of water and 25 ml of concentrated HCl. We will take the solution and we will add 5 gram of our steel mixture and we will heat it gently. Then few drops of standard potassium chlorate solution will be added. Because this KClO3 solution it will dissolve the carbides. The mixture is again boiled and we will boil it till we see that the clear solution is formed. So after this, then we will cool it down and dilute it by adding 50 ml of water. So from this solution, we will pipette out 2 ml of the solution and we will take it in a polarographic cell, and the supporting electrolyte here is 1 ml of 20% hydrazine hydrochloride solution, which will reduce the Fe3 plus to Fe2 plus. We will also take 1 ml of 0.2% cellulose, which acts as a suppressor, and 5.5 ml of 2 molar sodium formate solution. Now here the cell is kept in nearly boiling water bath for 10 minutes, and then after it is cooled the polarigram is recorded. So it will have this polarigram, it will have two steps. The first is the E half, that is the halfway potential, which is due to the reduction of cuprous to copper metal, and the second step is due to the reduction of lead. Now using standard addition method we can find out the concentration of lead and copper that is present in the steel. So this is how we can find out the amount of copper and lead that are present as impurity in a steel sample. So other industrial applications, determinations of polarography has been in the determination of traces of minor constituents. Like for example, it has been used in analysis of steel and ferroalloys for minor constituents such as copper, nickel, cobalt, manganese, chromium, molybdenum, tungsten, vanadium, tin, lead, and aluminium. It has also been used for analysis of copper base alloys, analysis of high purity zinc and zinc alloys, analysis of ferrous sulfate, analysis of aluminium alloys, analysis of pure aluminium, analysis of magnesium alloys, analysis of refined metallic tin and tin base alloys, analysis of metallic cobalt and cobalt salts, analysis of refined lead and lead based alloys, then analysis of nickel alloys and nickel compounds, analysis of cadmium metal, and analysis of zinc based alloys, and analysis of pure strontium salts. So as we can see, polarography is actually, it can be used for the analysis of the purity of various types of metals and metal based alloys. Then the next application is the determination of ascorbic acid, that is vitamin C, which is present in citrus juice by the standard addition and the calibration curve methods. So here ascorbic acid, it gives a very well defined polarographic oxidation wave. So the oxidation here it is shown in this equation. Ascorbic acid oxidizes to dihydroascorbic acid, and this oxidation wave is very well captured in the polarogram. Then calibration curve method. So how we will proceed in this method is, we will prepare a fresh stock solution of 50 ml of 0.2% vitamin C, that is ascorbic acid. We will prepare standard solutions of ascorbic acid in volumetric flasks of 25 ml. To each one we will add 0.5 ml of zero point 0.5 molar acetate buffer and different volumes of 0.2% ascorbic acid, 0, 200 microliters, 400 microliters, 600 microliters, and 800 microliters. So we will then dilute, and for each solution, we will record the polarograms over the required potential range. So when we plot the graph of the diffusion current versus the concentration of the ascorbic acid, then we can find out the amount of ascorbic acid that is present in our sample. Then how can we use the standard addition method for the determination of vitamin C in citric juice? So first we will take 10 ml of the juice from orange, grapefruit or lemon. Then we will filter the juice through a funnel having a pore size of about 1 mm. Then we will prepare 4 volumetric flasks. We will take 0.5 ml of zero point 0.5 molar acetate buffer, 2 ml of the juice, and standard addition of 0, 200, 400, and 600 microliters of 0.2% ascorbic acid. Now we will dilute our sample, that is to the mark that is in the volumetric flask, and then we will record the polarograms. We will plot the graph, and then we can find out the concentration of the ascorbic acid that is present in our sample. So now coming to the applications of voltammetry. So all these techniques, they can be applied quantitatively for the analysis of a large variety of samples, for environmental samples, steel samples. Now the choice of a particular technique, it will depend on the analyte's characteristics, expected concentration and other constituents of the sample. Pulse polarography is better for analyzing a wide range of inorganic and organic analytes, while the case of in the when we use the stripping methods, the analyte is to be pre-concentrated at the electrode surface. Further, the concentration of the analyte in the sample, the accuracy and precision required, it has to be depending on the technique that is to be selected. So the amount of separation between the potentials, that is the ID or the IP, diffusion current, or the peak current, this potential, it will depend on the type of the technique used and the concentration of the components. So if the difference is less, then minimum separation and there is overlap between the voltamographs, independent analysis is not possible, and simultaneous analysis method is to be followed. So here the analysis has been explained in details. Like in figure 9.1, we see the basic instrumentation of a voltammetry. So here it consists of two important components. First is a normal 3 electrode polarograph. Part is the linear scan voltage generator, which gives different types of signals. So here we see this is general representation or a general instrumentation of a voltammetric instrument. So here we have a working electrode, that is a micro electrode, mostly the DME, so whose potential is varied linearly with time. We have a reference electrode, that is whose potential is constant, that is mostly SCE or the silver chloride electrode. And the third electrode is the counter electrode, which is mostly a platinum coil electrode. So the potentiostat, it allows to impose the potential scanning between the working and reference electrode, while the current flowing through the circuit is recorded between the working and auxiliary electrodes. Then we have a keyboard that is attached with an analyzer and detector, plus a software which scans the data that is obtained. Then coming to the different steps involved in the preparation of samples and analysis in voltammetry. So for sample treatment, the sample must be taken in a solution form. If it is solid, it has to be brought into solution by dissolving in a suitable solvent. So mostly whatever the nature of the sample be, it has to be present in a solution form. Then coming to the addition of the supporting electrolyte. Every analysis has to be performed using a suitable supporting electrolyte, and the concentration must be 10 times than that of the analyte that we have taken. Then third step is the bubbling of the solution with an inert gas, mostly nitrogen is used. Fourth is the electrode cleaning. Then is the addition of our analyte. Then is the recording of the voltammograms, followed by measurement of peak height, drawing of the graphs, and then from the plot we will calculate the unknown concentration of the analyte. So this is how a how we can measure the basic steps in a voltammeter in a so these are the basic steps in a voltammetry. So now coming to application of cyclic voltammetry. So cyclic voltammetry is mostly here inorganic ions metal complexes are used which undergo electron transfer reactions without any bond making or bond breaking. So the most of the electrochemical reactions they involve an electron transfer group, and this is analyzed by CV, that is cyclic voltammetry. So the time scale of the this CV measurement is adjustable, and we can also adjust the scan rate. So there are several examples of coupled chemical reactions. With some of the two examples have been discussed. A cyclic voltammogram for the popular antibiotic that we call as chloramphenicol. Here it is shown in figure 9.2. This is how a cyclic voltammogram looks like. So the scan was started in the negative direction from 0 volt. So here in the x-axis it is potential, and in the y-axis it is current, that is measured in microamperes. So here the scan was started from zero point zero volt. Three peaks are observed. Peak A, here the peak A, we can see peak A, peak B and peak C. So the peak A, it represents the initial reduction, peak B represents the oxidation of a product of this reduction, and peak C for the oxidation of the product resulting from the events that occur at peak B. So here see, we can see here is the peak A, the peak B and the peak C representation has been shown. So to assist in the analysis of these steps, various samples of hydroxylamine and nitroso derivative have been used to confirm the assignment of peak B and C. So here it is the scan rate 350 millivolt per second has been used, and this is the structure of chloramphenicol. So there is another example where CV is used. It is in Thyronine. Thyronine is an ether which is also used. It is represents the combination of the amino of the amino acid tyrosine with hydroquinone. So here this is the in figure you can see its oxidative CV. Here it is shown in figure 9.3. Here it is shown the potential IE curve. So what happens here is the oxidative CV on a carbon paste electrode. Here in this case the scan is initiated from zero point zero volt. The initial two electrode peak, that is at peak A, it generates a proton and a organic cation which is hydrolyzed to benzoquinone. Here at point A it is hydrolyzed to benzoquinone and tyrosine. The tyrosine thus produced, it is oxidized to peak B. So we can see here it from A it comes to peak B. The benzoquinone is reduced on the reverse scan peak to C to produce the hydroquinone, and which is then again oxidized back to benzoquinone on peak D. So this is how we analyze a CV data. So these are the standard solutions of benzoquinone, hydroquinone. They have been also used to verify, to confirm the formation of these products at different points on the CV. So complex CV, so that is the cyclic voltammograms, they can also be analyzed, but it is quite a challenge. So that is why in for complex molecules mostly NMR has been used. However, CV plays a great role in understanding the structure of protein and many other inorganic complexes. So in summary we can say we discussed about the polarography, the applications of polarography, and also we discussed about the different steps of measurements involved in voltammetry and cyclic voltammetry. So with this we finished this unit. So the next unit is coming to the next unit. So this unit is about thermogravimetric analysis. So we'll just take a break of 5 minutes and again start with this new unit. So now we'll start with thermogravimetric analysis. So as the name implies, this unit it talks about thermal analysis and gravimetric analysis. So whenever we have gravimetry, we know that it is related to weight. So here the change in weight of a substance with respect to the influence of temperature or heat is called as thermogravimetric analysis. So first is we'll know about the instrumentation that is used in thermogravimetry, and the instrument is called as a thermobalance. So thermobalance it consists of several basic components in order to provide the flexibility that is necessary for the production of useful analytical data in the form of TGA. So here the curve as has been shown in figure 10.4. So first we will see here in 10 figure 10.1 it shows a thermogravimetric curve. We call it as a TGA curve. So here in figure 10.2, it shows a basic diagram of a thermobalance. So the basic components of a typical thermobalance is that it consists of a balance, a furnace or a heating device, a unit for temperature or measurement control that we call it as a programmer, and a recorder or a detector that records the change in the mass. So here all these components have been taken together and they have been shown in figure 10.2. So the balance is must be of high precision and accuracy because it measures the weight of the substance before and after heating. So the recording balances they are of two types. One is the null point and another is the deflection type. So the null point balance, it is more widely used. It has a sensing element which detects the deviation of the balance beam from its null position. A sensor detects the deviation and it triggers the restoring force to bring the balance to its original position. So the restoring force is directly proportional to the mass change. So whenever there is a deviation, the restoring force brings the balance to its null position. Then the second balance that is called as the deflection balance, it involves the conversion of the balance beam deflection about the fulcrum into a suitable mass change trace by a photographic recording, that is change in path of a reflected beam of light traveling light available of photographic recording. And the second is recording electrical signals generated by an appropriate displacement measurement transducer and an electrochemical device. So coming to the furnace and control systems, they must be designed to produce linear heating over the whole working temperature range. So a wide temperature range, generally it includes 150 degrees centigrade minus 150 degrees C to 2000 degrees centigrade furnaces. They have been prepared or manufactured by industries. So the range of the furnace it depends on the type of the heating elements or the compounds that are to be analyzed. Then coming to the temperature measurement and control, that is the programmer. The temperature measurement they are mostly done using thermocouples. The chromal aluminum thermocouple they are often used for temperature up to 1100 degrees centigrades, whereas platinum and 10% rhodium is used for temperature up to 1700 degrees centigrade. So depending on the range of temperature of our need, we can design the thermocouples. The temperature may be controlled or varied using a program controller with two thermocouple arrangement. The signal from one it actuates the control system, while the second thermocouple is used to record the temperature. Then comes the recorder. So graphic recorders, they are preferred to meter type recorders. The XY recorders are commonly used because they plot the weight directly versus the temperature. The present instrument facilitate microprocessor controlled operation and digital data acquisition and processing using personal computer with different types of recorder. So here in figure 10.3, it shows a schematic diagram of a typical balance and furnace assembly. So we have here in this diagram, we can see that the whole of the balance is present inside a glass to protect it from external impurities from the atmosphere. So there is a control mechanism to regulate the flow of the inert gas to provide inert atmosphere and water to cool the furnace. The temperature sensor of the furnace, it is linked to the program to control the heating rates, and the balance output and thermocouple signal may be fed to recorder to record the TG curve. Then coming to the TG curves or the thermogravimetric curves. So here the TG curves, they represent the variation of mass m of the sample with respect to temperature or time. So when we plot the mass loss downward on the y-axis and mass gain in the upward in the x-axis. So here in figure 10.4 you can see a typical TG curve. The mass percent here, it is shown in the y-axis, and the temperature is taken in the x-axis. So here we can see when the mass loss is there, it is shown in the negative direction, but if there is a gain in mass, then it is shown in the upward direction. So this is how we can understand the TGA plot. Now sometimes derivative TG curves are also plotted, and they are called as DTG, that is derivative TGA curves. This DTG curves, it measures the rate of mass change with temperature, that is dm by dt versus temperature. So in y-axis, dm by the dt is taken, and the temperature change and the temperature is taken in the x-axis. Then coming to the sources of errors in TGA. So there are a number of factors which can cause errors during the measurement of TGA. Now, if errors are present, then there will be inaccuracies and differences in our results. So that is why handling of TGA instrument must be done with great care. So these are some common sources of errors that might occur in TGA have been given below. So first is the Buoyant's effect. If a thermally inert crucible is heated when empty, then there is usually an chance of increase in weight change as the temperature increases. Now this effect is called as the change in buoyancy of the gas in the sample environment with the temperature. So in most modern thermobalances, this effect, that is the buoyance effect, has been neglected. Then coming, there is another source of error that is called as condensation on balance suspension. Suppose condensation of the sample, it occurs, then the mass of the sample will also be affected, which will also influence the TGA curve. So this is avoided by maintaining a dynamic atmosphere around the sample in the furnace, so that all the condensable product, they are removed away. Then another error might also arise due to the random fluctuation of balance mechanism. If there is any reaction between sample and container, then there is also a source of error. If the convection effect from furnace arises, so it also gives rise to error. Error can also arise from turbulence effect of gas flow or from induction effect from furnace. So here the errors of the type 3, that is the random fluctuation of the balance, they can be avoided if we handle the balance with great care. And the error 5, that is the convection effect from furnace, it can be avoided if we take a proper sample crucible that is made up of either aluminum pans or other quartz materials. So here the last three errors, that is the 5, 6, 7, they have to be considered during the design of the furnace and the balance. So these are the man-made errors can be removed during the design process, and the other errors, they can be removed with proper handling and care. So now calibration of the thermobalance is first necessary because most of the measurements are done in mass, and the temperature is a very crucial factor. So that is why the calibration of the thermobalance is highly required. So how the calibration is done? It can be done by adding known mass of the sample container and noting the reading of the chart. The for temperature calibration, the ferromagnetic standards, they have always used. So in a magnetic field, there these substances, they are showed detectable mass changes. The ferromagnetic standards, they are quite suitable for the temperature range from 240 to 770 degrees centigrade. So once the thermocouple is calibrated, then the TGA instrument is good to go. Then coming to the interpretation of TGA curves. So TGA curves of a pure compound, they are characteristics features of the compound. So using the TGA plots, we can relate the mass changes or the mass changes to the stoichiometry of the compound that is involved. So this can also lead us to directly know the quantitative analysis for the compound or the sample that we have taken. So let us consider the TGA curve of calcium carbonate. Here it is shown in figure 10.5. The temperature has been set from room temperature to 1250 degrees centigrade, and the bold line here in this figure, it indicates the TGA plot. So here in this TGA plot, it shows that calcium carbonate decomposes in a single step between 800 to 900 degrees centigrade. So beyond this step, we see from 800 to 900 degree 50, it forms a stable step, and that is the stable product is calcium oxide and carbon dioxide gases. It is liberated out. So we know when calcium carbonate is heated, it forms CaO plus CO2. Now, when we look into this figure here, there are three plots. One is A, B, and C. So if we look into the figure C, it indicates the percentage of mass lost is 44 between 80, 800 and 950 degrees centigrade. This exactly corresponds to the mass changes which has been based on the stoichiometric calculations. So here, and we can find out this. So similarly, we can see how TG curve is related to stoichiometry interpretation. Now we will see in next example how it can be used to compare the thermal stability of the material. So this is a comparison, and that is mostly for qualitative interpretation. So here if we look into figure 10.6, TG curves of four different polymers, five different polymers have been shown. One is PVC, that is polyvinyl fluoride, PMMA is polymethyl methacrylate, LDPE is low density polyethylene, PTFE is polytetrafluoroethylene, and PS is polystyrene. So we see five different polymers have been taken, and their TGA curves has been shown here. So looking at this curve, we can actually indicate the thermal stability of the polymers. So here we see the PVC is the least thermal, least stable, because the decomposition here started at almost 210 to 200 degrees centigrade. But when we look into polystyrene, it is stable beyond 550 degrees centigrade and it decomposes at around 600. So here, from looking at this graph, we can say polystyrene is more stable, thermally more stable than PVC. So that is how we can explain the thermal stability of different types of polymers from TGA plots. Then coming to the different factors which influence the TGA curves. So here we talked about mostly in TGA, we can talk first, we include the temperature and the mass loss. So here some of the main factors which affects the experimental results are some of the factors which might also affect is the factors of the instrument, such as furnace heating rate, the recording speed, the furnace atmosphere, the geometry of the sample holder, the sensitivity of recording mechanism, the composition of the sample container. Now, also the sample characteristics, they influence the TGA curves. Like first is the amount of sample, the solubility of the evolved gases in sample, the particle size, the heat of reaction, the sample packing, the nature of the sample, thermal conductivity. These are some of the factors which greatly influences the TGA curves. So these factors we will discuss one by one. So first is the furnace heating rate. So at a particular temperature, the degree of decomposition is greater, the slower is the heating rate, and thus it follows the shape of the TG curve. Now for a single stage endotherm, it has been found that TIF is greater than TIS, where F indicates the fast heating and S indicates the slow heating. So here it means that, suppose for example, calcium carbonate does not show any mass loss below 600 degrees centigrade when we heat it at a heating rate of 3 degrees centigrade per minute. So here the rate of heating and the furnace heating rate is greater. That is, if it is faster, then we see that the mass loss becomes more than in comparison to slow heating rate. Now coming to the recording or the chart speed. So the chart speed on the recording of the TG curve of rapid or slow reaction has pronounced effect on the shape of the TG curves. For a slow decomposition reaction, low chart speed is recommended for recording the TG curve, because at high chart speed, the curve will be flattened and it will not show the sharp decomposition temperature. So for a slow reaction followed by a rapid one at the lower chart speed, the curve will show less separation in the two steps than the high chart speed. Then coming to the furnace atmosphere. The effect of atmosphere on the TG curve, it depends on the types of the reaction, the nature of the decomposition products, and type of the atmosphere employed. The effect of the atmosphere on TG curve may be illustrated by taking the example of thermodecomposition of a sample of monohydrates of calcium oxalate in dry O2 and N2, and that has been shown in figure 10.7. So the curve of calcium oxalate in O2 and N2 atmosphere, here it has been shown. The bold line is for nitrogen atmosphere, and here the dotted line, it represents in oxygen atmosphere. So in the first part here, it is the dehydration reaction, so which involves the loss of water. Now this is unaffected in both the atmospheres, because dehydration means removal of water. So water can be removed uh, beyond 100 degrees centigrade in both the cases. So the degree that occur, then here it diverges beyond 400 degrees centigrade for oxygen. So we see the oxygen temperature here, it decreases, whereas and it then proceeds, and this region here, if we look at this 500 degrees 500 to 600, the oxygen curve again merges with the nitrogen curve, followed by a slight higher temperature beyond 700 degrees centigrade. So now here, this step beyond 800 degrees centigrade, 900 degrees centigrade, the total calcium carbonate, it has decomposed, and this step is not affected by O2 or N2. But still we can see there is a slight difference, and this slight difference may be due to the nature or composition of calcium carbonate, such as particle size, the surface area, or some lattice defects. So this is how we can see or study the different types of inert atmospheres or inert atmospheres or the normal gas atmospheres that is used in TGA, and we can study the influence of such atmospheres. Then the effect of sample holder in TGA measurements. The sample holders, they range from flat plates to deep crucible for various capacities. Mostly crucibles, they have been used. Generally, it is preconditioning that the thermocouple is placed on near the sample as possible, and it is not dipped in the sample because it might stick to the sample. So actually sample temperature is not recorded. It is the temperature at some point in the furnace near the sample. Thus, it leads to a source of error during this heating process. If the sensitivity of the recording mechanism is not enough to record the mass change of the sample, then this will also cause error in recording the weight change of the sample. Then coming to effect of sample mass. So the sample mass has the following effects. The first is the endothermic and exothermic reactions of the sample. It will cause sample temperature to deviate from a linear temperature change. The degree of diffusion of evolved gases through the void space around the solid particles, and the existence of large thermal gradients throughout the sample if it has a very low thermal conductivity. So therefore, it is always advisable to use minimal amount of sample as possible, and that indicates the sensitivity of the balance. Then coming to effect of sample particle size. The particle size will cause a change in the diffusion of the evolved gases, which will alter the reaction rate and hence the curve shape. The smaller the particle size, the greater the extent of the decomposition at any temperature. So when we use a large crystal, there is a very rapid mass loss during the heating. So this rapid mass loss will give rise to the errors during the teaching, during the measurement process. Now coming to effect of the heat of the reaction. The heat of the reaction will affect the extent to which sample temperature proceeds or succeeds the furnace temperature. So this depends on whether the reaction is exothermic or endothermic in nature. The other sample characteristics such as sample packing, the nature of the sample and its thermal conductivity will also affect the nature of the TGA graph. Now, if the sample reacts with the sample container during the heating process, then there is also a possibility of a change in TGA curve. So, hence, it is always advisable that we will choose a sensible sample container that will not react with our sample. Then coming to applications of thermogravimetric analysis. So TGA curves, they provide the information about the thermal stability of any material. So besides that, there are other applications. Some of the applications, they are used in purity and thermal stability, solid state reactions, decomposition of inorganic and organic compounds, determining the composition of the mixture, the corrosion of the metals in various atmosphere, the pyrolysis of coal, petroleum, and wood, the roasting and calcination of minerals. It is used in reaction kinetic studies, evaluation of gravimetric precipitates, oxidative and reductive stability, determining the moisture, volatile, and ash contents, and it is also used for desolvation, sublimation, vaporization, sorption, desorption, and chemisorption reactions. So we'll just discuss a few of the common applications of TGA. So first is the application of TGA in analysis of inorganic and organic mixtures. So first we'll talk about binary mixtures. So let us consider a binary mixture, that is mixture of two compounds AB and CD, and their characteristics TG curves has been shown in figure 10.8. So here one is AB and this is CD and this is the AB plus CD. Here two compounds AB and CD and their mixture, that is AB plus CD, it has been shown in the figure 10.8A and 10.8B, the TG curves. So the decomposition, we will look into figure 10.8a. The decomposition of the pure compound AB and CD, here they occur at temperature T1 and here for CD it occurs at T2. So the TG curve of the mixture of AB and CD, we can see the decomposition here. If we look into this, the plateaus, they begin at the same temperature as they start in that of the AB and CD individual. So here in the mixture we can see from where the AB starts decomposing, here it also starts decomposing, and where CD starts decomposing in the mixture, it also starts decomposing at that temperature. So we can also here notice that the mass overall loss overall up to T1, here it is xmg, and from T1 to T2 it is by ymg. So by measuring these two quantities, that is x and y, we can determine the quantities of AB and CD that is present in the original mixture. So such type of analysis has been done for mixtures of calcium and magnesium carbonate. Then coming to this analysis of mixture of calcium and magnesium carbonate. So here we can see this is a mixture, the TG curve of a mixture of calcium and magnesium carbonate. This is the total mixture and the TG curve it has been shown. So here we can see beyond 200 degree, after 210 degrees centigrade, the mass loss starts. This is before the 210 degree, the mass loss is due to the moisture. So another mass loss here, it occurs at 400 degrees centigrade. So that is because of the reaction of magnesium carbonate forming MgO and CO2. Now we know that the calcium carbonate, it decomposes about 800 degrees centigrade. So the mass loss between this region, that is 600 to 800 degrees centigrade, it is due to the decomposition of calcium carbonate. So the portion of the graph between this AB, it represents M1, and here between CD, it represents M2. So then in here we can then calculate the this AB and CD, and we can find out that then from this plot, the M1 minus M2 is the loss of carbon dioxide, and using this value, we will calculate the for decomposition of calcium carbonate. We know CaO is formed, and using this reaction, we can find out the exact value or the number of moles of calcium that is present in the mixture. Then coming to analysis of mixture of calcium and magnesium oxalate. So here it is the calcium oxalate. It is the measurement is very difficult because it has a tendency to gain moisture even at 110 degrees centigrade. So co-precipitate ammonium oxalate, it remains undecomposed. The anhydrous calcium oxalate is hygroscopic, but calcium carbonate is it can lose its water, and beyond 800 degrees centigrade it decomposes. So above 635 degree, the decomposition of calcium carbonate, it becomes significant, and it is completely converted to CaO at 900 degrees centigrade. So these are the figure 10.10. Here it shows both the derivative TGA curve and the TGA curve for the calcium oxalate. Here it has been shown. So three different steps can be uh, deduced. First is the removal of water from calcium oxalate. Second is the decomposition of calcium oxalate into calcium carbonate plus CO. Then finally is the decomposition of CaCO3 to CaO plus CO2. But this magnesium oxalate, it decomposes in two steps. Like first is the removal of water from magnesium oxalate, and then this magnesium oxalate direct it converts to MgCO3, and immediately it is formed to MgO. So because at 500 degrees centigrade, MgCO3 is unstable, and it immediately forms MgO. So the TGA curve, it has been shown here. At 500 degrees centigrade, the mixture contains CaCO3 and MgO. So after 500 degrees centigrade, there is only calcium carbonate present in the mixture, and around 850 degrees centigrade, this calcium carbonate, it decomposes and forms CaO, that is calcium oxide. So this is how we analyze a different mixture of calcium oxalate and magnesium oxalate. Then coming to the analysis of a mixture of silver nitrate and copper nitrate. The TG curve of pure silver nitrate and copper nitrate and their mixture, it has been shown in figure 10.11. This is A for silver nitrate, B for copper nitrate, and C is for the mixture. Now, curve A here, it represents typical silver nitrate, and the degradation starts at 473 degrees centigrade at this temperature, and after 600 degrees centigrade the decomposition is less, and here AgNO3 has been converted to AgNO2. Above 810 degrees centigrade, pure, here we see pure Ag metal is formed. So these are the two equations that are involved in the degradation of silver nitrate. Then here in second case, we have taken copper nitrate. So copper nitrate, here it gives a different types of, we can see the TGA curve. So first, up to 150 degrees centigrade to 200 degrees centigrade, this region is for moisture loss and loss of nitrogen oxide. Then we see after the 200 degrees centigrade, there is a decomposition at 278 degrees centigrade, where it has been shown that this copper nitrate has been degraded to copper hydroxide. The copper hydroxide, then it degrades to to copper oxide beyond this 278 degrees centigrade. So now if the mixture of this copper nitrate and silver nitrate they are taken, then the curve C is marked. Here we see the curve C is marked. Now here the horizontal related to the basic copper nitrates, but when we look into 240 to 400 degrees centigrade, this there is a residue which keeps the copper mass constant, because beyond 900 degrees centigrade already Ag has been formed, and here it is Ag plus CuO. So if M1 and M2 they are the mass of the sample at 470 degrees centigrade, then the amount of silver and copper can be calculated accordingly. So this is how we can calculate the mass of different metals that are present in a sample from the TGA plots. Then if we take a complex mixture, so here we will consider the analysis of a mixture of calcium, strontium and barium oxalates. That is, three different types of elements are present here. So in the thermogram of the mixture of Ca, strontium and barium, it is noticed here in figure 10.12. You can see this is how the mixture of calcium, strontium and barium oxalate looks like. So here we can see the between 100 degrees and 250 degree the moisture is evolved from the metal oxalates. The curve is horizontal from 250 to 300 degrees centigrade, which corresponds to the composition of the metal oxalates. Here the all three oxalates they decompose simultaneously at 500 degrees centigrade. From 500 degrees centigrade to 600 degrees centigrade, the anhydrous carbonates were stable. So on further heating, the calcium carbonate, we know it decomposes in the region of 620 to 860, which is followed by decomposition of strontium carbonate from 860 to 1100, at which after 1100 barium carbonate it decomposes. So here we can from this curve we can calculate the mass loss. First is the mass loss at 100 degrees centigrade is ms. M1 is the water of hydration, M2 is for the loss of CO, M3 for loss of CO2 from carbon calcium carbonate, and M4 is loss of CO2 from strontium carbonate. So then from using the values of M1, M2 and the respective masses, we can calculate the amount of the individual element that is present in the mixture. Now coming to the analysis of organic mixtures. So TGA also provides quantitative information on the decomposition of organic compounds. For TGA has been used to determine the amount of vinyl acetate that is present in copolymer of vinyl acetate and polyethylene. Now when vinyl acetate is heated, it loses acetic acid around 340 degrees centigrade. Here it has been shown. The TG curves has been shown here in 10 figure 10.13. The here what happens is the TG curves show that for several vinyl acetate polyethylene copolymers they indicate the loss of acetic acid at 340 degrees centigrade. Then each mole of vinyl acetate loses 1 mole of acetic acid. So then we know can calculate the amount of vinyl acetate which is present in the polymers. So here the calculation has been shown, and using this plot we can calculate the loss of vinyl acetate from the copolymer. Then coming to the gravimetric precipitates, it should be dried or ignited. So another important application of TG is in the determination of correct drying temperature for precipitates that is used in gravimetry analysis. It also provides information whether a gravimetric precipitate should be dried or ignited. For familiar precipitates, ignition temperature is generally based on practical experience. Like AgCl, it is dried at 130 to 150 degrees centigrade. Barium sulfate is heated at 800 to 900 degrees centigrade. So like in order to avoid this, we can basically make use of the TG curves. So the here the precipitate can be, it has been reported that the precipitate of aluminum hydroxide, it should be ignited at 1200 to 1300 degrees centigrades to get alumina. But with the help of TGA curve, we know that the precipitate may be ignited at 1030 centigrade to get the alumina. So this is how TGA curves can be used to know the drying temperature for certain precipitates. The TGA curve also indicates the distinction in the crystal, that is the elimination of water and ammonia at 30 degrees centigrade. So there is no possibility in weighing anhydrous beryllium phosphate. So beryllium phosphate can also be used for the temperature of drying beryllium phosphate can also be used. Thus, ammonium beryllium phosphate, it decomposes easily when it is compared to beryllium hydroxide. Thus, when we see that here, uh, so when if beryllium hydroxide is precipitated by ammonia with BeSO4, then the precipitate is washed and ignited to give BeO. So here, beyond at about 900 degrees centigrade, BeO is obtained. First, Be hydroxide is converted to BeO only at 900 degrees centigrade. So it is better to precipitate beryllium with ammonium hydrogen phosphate and then ignite to 640 degrees centigrade to form the beryllium phosphate. This TG shows that which temperature is more useful for the precipitate to be dried or ignited. Then coming to the use of TG curves in the analysis of polymeric materials. The thermogravimetric analysis, it has um, wide applications in polymer analysis. It is used to study the decomposition, oxidation, and different types of physical processes that are occurring inside a polymer. So the basic route by which a polymer degrades, it can be categorized according to the following mechanism. One is the main chain scission, the side chain scission, the elimination, depolymerization, cyclization, and cross-linking. So these are some of the processes by which degradation in a polymer occurs. So out of these six steps, only 1 to 4 they lead to change in the mass loss and they can be detected by TGA. So here in figure 10.6, so here in figure 10.6, the TGA plots of 5 different polymers were studied. The polymer degradation, it started for we studied that for PVC, it has a very lower polymer degradation temperature, whereas the polymer degradation temperature for polystyrene was more. Hence, we can say that polystyrene is more stable than PVC. Then coming to the uh, study of kinetics using TGA curves. So TGA curves has also been used to understand the reaction kinetics that is happening inside a reaction. So this involves analyzing the shape of the TGA curve. So in general, we know that the rate of a reaction is proportional to the slope of the curve. But since there are various uncertainties, these analysis, they are sometimes difficult. So both isothermal and dynamic methods, they have been used in kinetic studies. But the isothermal method at elevated temperature has been it for a it has been used because it is much simpler in nature. The temperature dependence of a chemical process, we know it is expressed by the Arrhenius equation, that is K is equal to A into exponential minus EA by RT, where EA is the uh, here activation energy and capital A is the Arrhenius constant. The Arrhenius parameters, that is the A and EA, they measure the magnitude of the energy barrier, that is the activation energy that must be provided to the molecule for the chemical reaction to occur. So the rate constant K, here it is given as by d alpha by dt, where and the extent of conversion or fraction reacted decomposed is given as alpha. So here the general relation to describe the relationship is d alpha by dt is equal to K into alpha to the power m into 1 minus alpha to the power n. So here In equation 10.10, it is derived to various subclasses of rate equations such as first order, the nucleation, or the growth decay reaction by changing the values of m. So here is a simpler approach is to substitute the reciprocal of the isothermal lifetime of the rate constant in equation 10.9, and then we can extrapolate the data. The isothermal measurements, this have a limitation that of being rather time consuming. There are also difficulties in bringing the sample and apparatus to the required temperature without some decomposition of the sample having already taken place. So one way of avoiding this problem is to change a rate controlling variable during the course of measurement. So here TGA, the jump in temperature can be recorded by TGA easily, and it is given by the equation that using EA, that is the activation energy in 10.11. Here the dm by dt represents the rate of mass loss at temperature T1 and T2 that can be obtained from the TGA plots. Here the most of one of the popular method is described by Ozawa, Flynn and Wall, and in this method the separate measurements have been carried out at different heating rates at which the temperature is set against a particular mass loss. These are then plotted against dt by dt, and this equation in 10.12 is observed. So thus it is possible to predict the lifetime, let us say 10% of a mass loss as a function of temperature. So now apparently using the value of dt by t, we can modify the EA energy that has been shown in 10.11 to 10.13, and it is given by the equation in 10.13. Here T average is the average thermodynamic temperature, and T amp represents the amplitude of the temperature modulation, and capital L is the logarithmic of the amplitude of the rate of mass loss. So here the general kinetic models that is used in TGA have been shown here in figure 10.2. The main difficulty in studying kinetic analysis in using TGA is deciding which number of equation and what it should be used for the calculation. So here figure 10.2, some important rate equations that are used in kinetic analysis, it has been shown here. So first, for the diffusion control processes, we can use one dimensional equation, and this is the differential equation that is used. Similarly, for a sigmoidal alpha time curve, we have this Prout-Tompkins model, and the equation used is this. So for a zero order equation, we can use d alpha by dt is equal to kc. First order is d alpha by dt is equal to k into 1 minus alpha. Second order is equal to, that is used when d alpha by dt is equal to k into 1 minus alpha square. This is the differential equation that we can use. So other equations, they have been shown, that both the differential forms and their integrated equation forms have been shown. So fitting our data to these equations, we can predict the nature of the curve, or the, and then we can find out the order of the rate of the equation. So this is how TGA can be used in understanding the reaction kinetics. So in summary, so we talked about the principle of TGA, the instrumentation and the various applications of TGA. The also the sources of error in TGA instrumentation has also been described. So with this, we complete the unit on thermogravimetric analysis. Now we'll talk about the about differential thermal analysis, that is DTA, and differential scanning calorimetry and different types of thermometric titrations. So before we proceed in this new unit, we'll just take a break of 2 minutes and again resume with this chapter. So now we'll begin with differential thermal analysis, that is DTA. We talked of TGA, that is thermogravimetric analysis. Here it is DTA. The technique is DTA, and as the name implies, it is differential thermogravimetric thermal analysis. That is delta T. The difference in temperature here it has been noted. So first we'll have a basic introduction to DTA. So it is one of the most versatile techniques for identification, and particularly in the case of novel materials or soil analysis. Here in figure 11.1 we see a typical DTA curve, that is in y axis we have delta T, in x axis we have T. But here in DSC, that is another technique, it is called as differential scanning calorimetry. We measure the flow, the heat flow in y-axis versus the temperature in x-axis. The DSC it will be discussed later. So we'll now focus on DTA. The chemical or physical changes which are not accompanied by mass loss, they are not indicated in TGA, but they are, there is a very likelihood that these changes may be indicated in DTA. So coming to the principle of DTA. Differential thermal analysis, it is a technique in which the temperature of the substance that is under investigation, it is compared with the temperature of a thermally inert material, mostly alpha alumina, and it is recorded with the furnace temperature as the substance is heat or cooled at a particular rate, scanning rate. The range of temperature measurable in the course of DTA, it is much larger than the TGA. So thus during TGE, so crystalline transition, glass transition reactions, the crystallization temperature, here they could not be indicated because it provided no change in mass. But these changes, they could be indicated by the DTA studies. Now since DTA is a dynamic method, it has to be standardized in order to obtain reproducible results. So this include the pre-treatment of the specimen, the particle size, the packing specimen, and other composition of the of our sample. So the principle of this method, it consists in measuring the change in temperature that is associated with the physical or chemical changes that occurs within the sample during the course of the heating or during the course of the proceeding of the heating process. So the thermal changes due to fusion, crystalline structure inversions, dissociation or decomposition reactions, redox reactions, they are all accompanied by either a rise or fall in temperature. So hence these are all recorded in DTA in the terms of delta T. So mostly the phase transitions, the dehydration, reduction, and other types of reactions, uh, they produce endothermic effects, whereas the crystallization reaction, oxidation reaction, they produce exothermic effect. So in DTA, the sample that is to be examined, it is placed by the side of a thermally inert material, that is the reference material, that is alumina in the sample holder. The temperature difference between the two is continuously recorded as they are heated. The block is heated in the electrical furnace, that is, they are both heated under identical conditions, and the difference in the temperature of both the samples, that is the sample, our sample, and the alpha alumina, that is the reference sample, they are recorded simultaneously. Then coming to the characteristics of DTA curve. So in a representation of a simple DTA curve has been shown here in figure 11.3. So in delta T, that is in y-axis, and the temperature, that is in x-axis. So the endotherms that are pointed downwards, the peak that point downwards are the endotherms, and the peak that point upwards, they are the exotherm. So here C is the exotherm and here F is the endotherm. So the temperature of the sample is greater for an exothermic reaction, and we know that for endotherms the temperature is less than that of the reference. Then when no reaction it occurs in the sample material, then the temperature of the sample remains similar to that of the reference. This is because both the reference and our sample, they are heated at exact conditions. Now when the reaction starts, so when if there is no difference, that is the delta T, that is the T of the sample, the temperature of the sample minus the T of the reference is 0 when there is no reaction. But as soon as the reaction starts, the sample might either be cooled or it hot depending upon the exothermic or the endothermic reaction. So the peak develops on the curve of the temperature of delta T. Now here we look into 11.3, the above figure again, and we see that along the AB, here along AB, there is no reaction. So it is flat. There is no change. But as the temperature is increased, here the B is reached to point C. So this indicates a exothermic reaction where the maxima occurs at point C. Then after point C, if the temperature is again increased, here it the peak C here, it corresponds to the maximum rate of heat evolution. So here this position C does not have much significance in DTA experiments. Then if we keep on heating, the our temperature is increased gradually, the delta T comes to D. Then ultimately there comes a point here we have the peak, the endothermic peak occurring at F. So this point is of much importance, and this is the endothermic peak which gives us the endotherm, and here it shows the melting temperature of our sample, and it is generally called as Tm. So here we can see if the we look into this factor, if we look the endothermic reaction, the peak EFG, it will be obtained. So this peak shows that it will be negative because the heat is absorbed. Now we see that the levels of the baselines of the exotherm AB and DE, they are both above the x-axis, that is AB and DE, that is both above the x-axis. So this is due to the fact that heat capacity of the sample has changed as a result of the exothermic process. So DTA curves, they not only help in the identification of materials, but the peak area, they provide the information regarding the mass of the sample and delta H, that is the change in enthalpy during the process. So such and other factors such as sample geometry and thermal conductivity. So here, if the two factors, they are expressed by a constant k called calibration factor, then the peak area is calculated as delta plus minus delta H into m into k. So positive sign is used for endothermic reaction when delta H is equal to 0. That is when the temperature of the sample will be behind than that of the reference. And the negative sign for exothermic reaction, that is delta H less than 0. That is the temperature of the sample, it will exceed that of the reference, and K is called as the calibration factor, which is temperature dependent. So once we know the value of K at a particular temperature, then the peak area can be used for quantitative analysis to determine the mass of the sample. Besides, the DTA curve also helps in estimating the heat capacity of a sample. So the heat capacity, that is delta Cp, it can be measured by this equation, that is 1 by heating rate into m, or we can say d by d dt by m into 1 by m. So this is how we can use DTA curves for the measurement of Cp. Then coming to the instrumentation. So here in figure 11.4, this is a block diagram of a DTA analyzer. So here it consists of four basic components, that is a furnace assembly, a sample and reference holder with temperature detector, a temperature programmer, an amplifier and a recorder, and an atmospheric control equipment and a sample holder. So the instrument measures the differential temperature of the sample as a function of time. So coming to the heating source. So here in DTA, the Nichrome, that is an alloy of nickel and chromium. They nichrome furnaces, they are used because they can sustain temperatures up to 1300 degrees centigrade. Platinum and alloys are used for higher temperatures, and molybdenum for temperatures ranging above 2000 degrees centigrade. Then coming to the temperature, so depending on our use, we can design the source of heating. Then coming to the temperature regulating system. Uniform rate of heating the furnace is ensured through electronic temperature regulators. The specimen holder needs to be highly specific in nature. They are mostly made of platinum, nickel, stainless steel, silver, and also alloys of platinum and rhodium. Even ceramic materials such as sintered alumina, silica, or heat resistant glass, they have been used for the preparation of the specimen holder. Then measurement of temperature. So rare metal alloys such as platinum or rhodium, they are commonly used for the thermocouple for measuring the temperature. When we need temperatures for exceeding 2000 degrees centigrades, tungsten molybdenum thermocouple, they have been used. The temperature recording system, they are now, for nowadays, automatic pen and ink electronic recorders have been found, and they record the temperature more accurately. Then controlling the recording of the heating curve. When a sample is heated at a constant rate, the temperature function is linear up to the moment when the sample undergoes the change, and then the slope represents the rate of heating which has to be remaining constant. So at the moment when an exothermic or an endothermic change takes place, the shape of the curve here changes, as here it is shown in figure 11.3. So the shape of the curve, it changes. Then once the exothermic reaction, it causes an increase in the heating rate, while we know that an endothermic reaction, it decreases the heating rate. So the main disadvantages of this method is its sensitivity, because small change in temperature, it will influence the observed data. So small temperatures, even minor temperature changes that are occurring within the sample, they are not detected. So that is why detector thermocouples, they are opposed to each other. So that is why they can be detected using voltage amplification. Hence very small sample size they are used in this process. So there are various factors that influence the DTA curves, DTA curves. So first is, the factors have been divided into two groups. One is the sample factors and other is the instrumental factors. The instrumental factors, such as the size and shape of the sample holder, the material with which the sample holder is prepared, the heating rate of the sample, the sensitivity of the recording system, the location of the thermocouple, and the type of the gas that is used for the measuring of the instrument, they all play a vital role during the measurement of the DTA. So most of these factors, they are associated with the instrumental design. So these factors, they have to be controlled during the manufacturing process. The sample factors, they include the amount of the sample, the particle size, the packing density, the heat capacity, the conductivity, the swelling and shrinkage of the sample, and these are the some of the factors which need to be considered in order to avoid any errors during the DTA measurements. So first is the amount of sample. So we know in DTA analysis, the peak area of DTA curve, which is proportional to the mass of the sample. So here in DTA experiment,
Madam,
huh,
is it different from TGA? This machine is different
yes,
from TGA.
the machine is not different. You can calculate. There is a machine called as STA, simultaneous thermogravimetric analyzer. Okay, that machine, it measures DSC, DTA, and your TGA.
No, I have seen DSC machine. I am
Huh.
handling also DSC, and
I'm telling
I
you
am also handling
STA.
TGA also.
No,
But
there comes a machine. It is called as STA.
Perkin Elements is providing DSC and TGA. There are two
Okay.
different machines.
I
But
understand, but I am telling there is a machine from, even from Perkin-Elmer. You can see it is called as STA,
Achha,
simultaneous Thermogravimetric analyzer, STA. It does the both of this work.
Okay.
That is why it is
All
named as
three,
STA.
all three, DSC and
Yes.
TGA and DP.
See, yes, yes. See, you can measure the TGA, the DSC, and from the plot, it will also give you the DTG plots, the DTA plots, and everything. It is called as STA. We have one in our institute. It is STA. If the
Is it
one from
available in Odisha?
Continental. Sorry.
Is it anywhere available in Odisha, any institute?
Yes, yes, yes. It is available in Odisha.
In
There
Odisha,
are
means
many institutes you can see who are working with this materials chemistry.
IMMT.
IMMT, I guess. Yes, they have STA, I guess. But it's not working there.
Acha, it is available in CPET.
Yes, CPET they have.
Okay, madam. ठीक.
Okay, STA is there. Yes.
Okay.
Even you can check in NIT Rourkela. They have one in Metler Toledo. That is a very sophisticated instrument there in Rourkela.
Okay. Okay, madam.
Okay.
Thank you.
Hmm. So the amount of sample also influences the DTA analysis. So here the peak area of DTA curve is proportional to the mass of the sample. The particle size also influences the DTA measurements. The packing of that is the sample packing also influences the DTA curves. The heating rate, that is the scanning rate. So mostly when the scanning rate highly influences the DTA curves. So what we do is, in most of the cases, we prefer to keep it as small as possible, mostly in the range of 3 degrees to 5 degrees per minute. So the atmosphere around the temperature, that is whether nitrogen atmosphere or oxygen atmosphere, they have a great role to play in determining the DTA curves, and simultaneously it influences the nature of the endotherms. So here in table 11.1, the factors that influence DTA curve, it has been tabulated. So here, if we look into the influence of heating rate, it causes a change in peak size and position. And the suggestion is that we always use a low scanning rate. So some of the factors, they have been listed with its effect, and the suggestions for improving this have been provided here. Then coming to the sources of error. There are number of source of errors in DTA, as they can lead to inaccuracies in the recorded temperature and the weight data. For some common sources, our first is the Buoyancy effect. So if the crucible is, is heated where there is usually a change in the mass, then the temperature arises. So this is what we call it as the buoyancy effect of the gas. But the instruments that we are dealing with, they have now this negligible buoyancy effect. So first, to however to run to eliminate any source of error, what we do is we run a blank sample. So then we go for our actual measurement of the sample. Then condensation on temperature sensor. So the condensation of the sample around the thermocouple will also influence the DTM.
Madam, you are not audible. Hello.